Good afternoon, everyone. It's a real distinct pleasure for me to actually kick off the ceremony this afternoon to honor the recipient of this year's Russell L. DeSouza Award. Just by way of background, this particular award is given to individuals whose energy, expertise, and active involvement enable the Unidata program to better serve the geosciences. Honorees personify Unidata's ideal of a community that shares data, software, and ideas through computing and networking technologies. And since the beginning of Unidata, like I mentioned this morning, the program has benefited from the commitment of a number of individuals, and this particular award is named after Russell L. DeSouza, who was a faculty member at Millersville University, and whose involvement and contributions to Unidata were exemplary, and we are actually honoring Russ. Russ became actively engaged with Unidata the same day I started with Unidata on the users committee. We both were the first batch of committee members on the users committee going back to 1989. And quickly, Russ was such a committed community member. He contributed a lot to the advancement of Unidata. And in 1990, the Unidata program asked Russ to serve on the policy committee, but continued to be a liaison to the Unidata users committee. And Russ contributed immensely over the many years he was associated with Unidata. He always brought the concerns and the issues that impacted small programs. And at that time, Millersville was actually a small program. And today you wouldn't even know it because they are so well known thanks to the groundbreaking work Russ DeSouza did in that particular program. One of the first things Russ did on the users committee was commit his university to serving as the program that determined every single day where the satellite floater segment should be pointed and the data extracted and distributed to the community. So they monitored the weather every single day and actually sent a notification to the program center which will extract the satellite data for that particular day and distribute to the community through the Unidata Wisconsin channel. He then continued a similar effort when the NextRad data became available to the community with the NITS program that was instituted in the early 90s. Then in the mid-90s, Russ actually had to resign from the policy committee to concentrate on his treatment from malignant melanoma. And he battled that like he always did, with grace and a lot of humor. He officially retired from Millersville faculty on May 17, 1997, and he died on June 6 of that particular year in 97. And this particular award is given to individuals who personify the work that Russ DeSouza conducted over the many years. And I'm going to turn this over to Kevin to introduce today's recipient of this award, which has been given for the past almost 15 years now to individuals in the Unidata community.
Thank you, Mohan, and I'm very pleased to present Rich with this year's award. A little bit about Rich. I guess we could maybe term his journey as from wolverines to snakes, and we can understand that as Rich actually got his bachelor's in atmospheric and oceanic science at the University of Michigan, and continued on to get his PhD in physical oceanography at the Woods Hole Oceanographic Joint Program with Massachusetts Institute of Technology. He has worked at USGS since 1989, I've got, including 3 years spent at NATO in Italy, believe it or not. So I imagine that NATO is actively using NetCDF all these years. I did not know that. So in terms of the award presentation, again, this recognizes your service to the community. And so for your dedication, enthusiasm, and inspiration that truly reflect the goals and ideals of the Unidata program, we here on behalf of the Unidata Users Committee, we very proudly present you, Rich Signell, with the 2014 Russell L. DeSouza Award. For more than 20 years, your tireless effort to promote NetCDF as a standard storage format for numerical ocean model data have led to significant increases in its adoption in the geoscience community. And coupled with that is your advocacy for the climate and forecast metadata conventions, the NetCDF markup language, the THREDDS data server. Your efforts have led to improved data usability and interoperability across a wide range of the geoscience disciplines. We also recognize your vigorous advocacy for using the Python language, there's the snakes, in scientific workflows, and for encouraging the Unidata program to increase its support for use of this tool by the geoscience community. So for all of us here, very proud to present you with the 2014 Russell L. DeSouza Award. So let's have a big round of applause. And all we ask is that Rich provide a talk, and it's something that he's a little bit good at. Usually it's unsolicited, and he always has some great little presentation. So I imagine more to follow very shortly. So thanks again, Rich.
All right. Thanks very much, Kevin. Let's see here. Yeah, it is. It's exciting to receive this award, especially from you guys, because I think I mentioned before. I always thought you guys thought I was kind of a pain in the ass, and so it's really something special, and maybe it'll allow me to keep doing this stuff a little bit longer. So yeah, I'd like to talk to you about all those things that Kevin mentioned today in this talk, and it's been really exciting working on this. There's a lot of I don't go out promoting Unidata technology. I go out promoting what I think is really useful technology for the community. And it just happens that Unidata happens to, makes a fair amount of that software. So you'll see that in this talk today. I'm going to talk to you about ocean atmosphere climate model assessment for everyone. What that means really is trying to take model assessment from the hands of a few specialists and put it in the hands of people who actually know the science, make observations perhaps, or maybe just the general public, smart people from the public that maybe don't run models, but know how to use some software. And if we make that easy enough, that becomes possible. So, this slide here is basically showing the kind of thing we want to be able to do. We want to take model A and model B and compare it to some data in the third panel here. And this plot was actually produced, as you can tell, in Matlab, but it was pulling data through OpenDAP from one server, and here from another server, and here from another server, but all using identical commands in Matlab to pull those two models and pull the data, even though these models were using different conventions, different variable names for latitude and longitude, and different vertical coordinates and things like that. And so once you get it in a tool like this, be it Matlab or R or Python, then you have the data here. You not only can make plots with the same color scale, but you can do all kinds of quantitative analysis. And I'll tell you about some of the stuff that we've been doing lately as part of the Integrated Ocean Observing System. So before I do that, I want to just return briefly to when I saw that announcement and it said I'd been working on this stuff for that long. I went back and found this paper. Actually, Russ gave me the link, and then I tracked it back, and indeed, we had this paper, Harry Genter and I, who's actually at the USGS now in Reston, and still using NetCDF. We wrote this paper together in 1990. Actually, in 1991, we gave this talk. So I just wanted to, is anybody like born after 1991 here by any chance? Because I asked this question actually at a workshop 2 weeks ago, and a couple of people raised their hands, and I was like, so now I can say, I've been doing NetCDF since before you were born. I always wanted to say that. I guess it's going to get better and better, right? So, this little paper, but it's been a long journey. For the last several years, as I mentioned, I've been working in this context of this U.S. Integrated Ocean Observing System. So I work at, USGS pays me to be part of this program, which consists of 17 different federal agencies and 11 regional associations all around the U.S. And this program is kind of cool. The idea is that in each one of these regions, they all have local issues that are important for their ocean environment. So it might be red tide up here, it might be oil spills down here, might be, surf forecasts or aquaculture issues, in these different regions. And they all have, and the idea is that you can take a whole bunch of people who are making observations, and by providing an infrastructure and some organization, they can work together and share data, share model output. So in each one of these regions, there's multiple ocean models running, often coupled atmosphere ocean models, so several different MET models, and then observations. And so they have this problem of how do we deal with all this data in an effective way for our users. So people want to, there's a lot of models running, but as when something happens, or we want to know how well these models are working to address issues like Hurricane Sandy, this dramatic picture of the waves crashing in on Ocean Grove Pier in New Jersey. How well are the models predicting wave environments like this and water levels from these kind of events? Which models are working better? Why are they working better? These are tough questions to answer when these models are just on different websites using different formats, and it's really difficult to get at that information for a lot, and for that reason, a lot of this stuff hasn't been looked at before. People do some metrics on their own model, but they don't compare them to other models. And when Deepwater Horizon hit, there were about 6 different models running, and nobody had any idea of what their skill was to look at surface currents or subsurface currents. So the IOOS core principles are to adopt open standards, so OGC, ISO, and Unidata community standards. Avoid stovepipes, obviously. And each person who wants to contribute, if they have data data from observations or models, they need to provide a standard web service. And everything built for the customer is going to be consuming those web services. So that's kind of forward-looking. And then we have these issues to deal with. So ocean grids are not regularly spaced. This is a vertical coordinate. This is the vertical mesh in a typical ocean model, so stretched from the top to the bottom. And this surface actually goes up and down with the sea level, like on the tide. So it stretches those vertical levels over the water column. And then you have these curvilinear coordinates, so everything is not on a uniform lat-long grid. So that's one issue you have to deal with. Another issue is you have these unstructured, or we call them unstructured grids, but often triangular connecting to rectangular grids, so quads and tris in the same mesh. And these are designed to represent these little gaps, like this is actually Woods Hole, Massachusetts, so I live in here somewhere. But to represent the flow through these little passages, you either need to do nesting or you need to have something like this unstructured mesh. So these are becoming more and more popular in oceanography. I think they're becoming more popular actually throughout the field. Actually, if you look at the next generation NCAR model, it's a hex. I think it's a hex-based model. And in groundwater, for years and years they've been regularly gridded, but now they're moving to unstructured grids as well. So this is going to be a bigger and bigger issue as time goes on. So, we also have data from buoys. We have data from ships that are running around. We have data from these ocean gliders that sort of, seesaw through the ocean, adjusting their buoyancy and sort of fly upwards and down, taking transects. So this is the kind of data that we collect in the ocean. we need to deal with that stuff as well. And as I think most of you guys know, obviously the climate and forecast conventions provide a solution for how to describe the data from those different kinds of data sets. Unstructured grid, structured grid, those different kinds of observational data sets. Time series, trajectories, and collections of those things all are described by the CF conventions. But of course, you have to you have to put that metadata into your NetCDF files. So for unstructured grids, we have these UGRID conventions that we just actually versioned last year. So these are meant to go into CF eventually, or perhaps they'll just stay as UGRID conventions. But they tell you how all these triangular grids are connected, so that you can describe those in a uniform way as well. So and nCML turned out to be a huge boon for getting this kind of work done, because instead of telling people that they had to go fix all their output, which isn't a good sell, that's not usually an easy sell. You could say instead, hey, we will help you. We will look at your output, and we'll write some nCML for you that will standardize and CFIze your data. And so in this case, we're actually taking a whole huge collection of files, and all the water levels were written into individual NetCDF files, and all the wave heights were written into a collection of other NetCDF files. And this is aggregating all these significant wave height files over time, and aggregating all these water levels over time, aggregating everything, all those into a union aggregation, so putting all the variables and all the different files for all the different times into one data set, and then we're changing some of the attributes. We're adding a standard name of barotropic northward seawater velocity. We're telling this variable what the coordinates are. All this stuff is happening in nCML, and the user, all they had to do was drop their 150 weirdo NetCDF files into a directory, and we're done. And and this group, they did everything the same, right? It's not like we have to generate a new nCML for every collection pile of data sets that represented a logical data set. All they had to do is change like one or two lines in here. They may not understand any of this junk, but they could change the line that said title and the one that said summary, and maybe this this string down here which had a different name. So they don't have to know everything about all these standards in order to get their stuff served in a standard way. So this is I love this figure. So this is what we basically use. So we have all these weirdo files over here. Actually they're not weirdo. They're at least NetCDF or GRIB or something, but they don't necessarily use these conventions. And then for each one of these models, we have one of these little nCML templates essentially that translates all that stuff into a common data model. And and the new thing has been this observational data that we're now feeding in and handling in the same way, either through nCML or just writing them as CF compliant to begin with. So we can handle in this sort of everything, all these weird things funnel into a common data model inside this black box, which is the THREDDS data server. And once it's inside here, you can deliver it out through all these different services, some that have been developed from the start by Unidata, and others that have been added, like nCISO, which we actually added. The community, the IOOS community added so that you could get ISO metadata out of this attribute information in the NetCDF files. So we have OpenDAP with CF conventions. That's what we use for all these unusual model outputs. But then if you have regularly gridded output, you can use WCS. The sensor observation service was added. This is an OGC standard for observational data. So you do these requests for like a particular, you say, describe this sensor, and it'll tell you some metadata about the sensor, and then you say get data, and it'll give you back the data in the specified like time range and things like that you request, and with different kinds of output formats. So these two, OpenDAP plus CF and SOS, are the ones that IOOS is promoting for its observations and for the model output. And for cataloging, this nCISO, so ISO metadata, the ISO metadata then flows into a catalog service. And there's a bunch of these guys out there. So the question is, okay, so great, you've got this thread server, but you don't have one thread server. You have, 20, like we have 25 or so in IOOS. So how do you find data across all those thread servers? So you could make, in the old days, we would go, okay, well, we'll make a master threads catalog, and somebody will maintain it, and we'll try to point to all the other catalogs. That's not scalable, and it's not, and it breaks, and somebody, person who maintains it goes away. So instead, you create this, you take the nCISO records and you put them into one of these catalog servers. We started out with GICat, and then GeoPortal server, and now we're actually using quite a bit the CCAN PyCSW. All these things, they harvest ISO metadata, and they put them in a database, and they allow you to query that database then to get back the data set information. So I'll show you how that works in a second. And for OpenDAP with CF, of course, we know there's lots of tools, a lot of them based on NetCDF Java that can consume these. We wrote a Matlab tool called NCTOOLBOX that sits on top of this for Matlab users, but of course there's NetCDF for Python that goes to Python and other tools as well. So you get your data up there, and of course you can use things that are already built into threads like nCWMS. So you can browse with Godiva 2, and this was showing was this Arthur? August 28th. This was the big storm that was coming up the coast at the end of August that went offshore, but these are wave heights. Just showing again. Once you throw your stuff up here, you can use tools like obviously that have been developed elsewhere, like this one, Reading eScience Center, to display the data. It just comes for free by putting your data in CF conventions and turning on your WMS service. You can also use this Matlab toolbox that I was describing, which sits on top of NetCDF Java. You can go to GitHub and grab it. You can do things like nj-tslice. This is a very high-level function. You give it a URL, a variable, and a time step, and it gives you back two structures, one that's data and one that's the geospatial information. So in this case, we did a 3D subset at a particular time step, right? So we get back a 3D structure, 22 levels, 120 by 180 lat-lon, and then we get back this geo object, which contains the latitude, the longitude, the z array for that particular time step, and a MATLAB, and whatever the original time units were, it gets converted into a MATLAB datenum. So now anything that is CF compliant, you can just point a URL, give it a variable name and a time step, and it returns to you unambiguously this structure. And this, then you can just use, you can query any model you want and get back that data from that model. So we did the same thing that we developed this UGRID package that currently sits sort of outside of the threads distribution, but it allows you to work with these unstructured grids by opening them like nCUGRID, and then you can query and get back not only latitude, longitude, and time, but also this connectivity array that allows you to put it into a tool that requires that connectivity array for like drawing a contoured surface or a shaded color shaded fill plot on an unstructured grid. So then you can do this kind of stuff that I showed in the title slide. So for model output, just to show you that we can do cool things with 3D with this toolbox, this is a picture from IOOS showing this web app that they built where the user goes in and they see where one of these little gliders is running around in the coastal ocean, and when you click on it, you get a little, a bunch of little icons popping up, and if you click on a thumbnail, you get a bigger plot. Well, on this thing, you can actually also click and get the OpenDAP URL for this glider, and if you then do that and you pop it into NCTOOLBOX, on top is shown that same glider path just being displayed in MATLAB, and below that is the same glider path virtually done through 3 different models. So we're flying the glider through the model in space and time and pulling out these transects. So this is actually well, it doesn't show here, but it's okay right here. This is from September 11th to September 20th. So this is an 8-day period going along here. So it's actually pulling data from at each, it's doing the interpolation in space and time to come back with these transects. This is a big pain in the butt. In fact, this had never, been done before we had this tool, and this tool makes it really easy. And so armed with a tool like that, some scientists, who just installed NCTOOLBOX came along and used this to do these analysis on a bunch of models, all through the Mid-Atlantic Bight. And they did a quantitative analysis that ended up having some fundamental insights about which one of these models worked well in different conditions. And so just enabling these tools allows science that was, could never have been done before to be done and make it pretty easy. And this is just an example of comparing 3 different unstructured grid models again, just using identical commands to pull in water levels for Hurricane Ike and just plotting them. And these are, if you go get NCTOOLBOX, if you're a MATLAB user, you can just use, you can just run this demo and it'll reproduce this. And of course, you can use tools like the IDV. This is showing a salinity isosurface in the Gulf of Maine. on top of color shaded bottom temperatures, and then with some WRF streamlines on top. So one thing I just actually thought I'd mention just for this crowd, I don't know if, it seems like not that many people are aware of the subset service as point. And so I just thought I'd mention it because it's pretty cool. We use this quite a bit because we often get people who say, who are just Excel users and they just want some model output. And before we would just like tell them to go away. But now we can really easily give them a tool where they can actually use themselves to pull the data from the model at a particular grid cell. So if you have here we have a model output, which is actually our coastal forecast model for the East Coast, which actually is a coupled ocean, wave, and sediment transport model. Two-way coupling between all that stuff. And the links down here, if you click on the NetCDF subset link, you get up this page. Actually, no, you don't get this page. You get the NetCDF, the traditional NetCDF subset page, and then if you click on the thing that says point data set instead of gridded data set, you get this page, which is kind of like a lot of people don't even notice that is there, that's a link. And so anyway, if you click on that, and then you get to this NcGrid as point data set, then you can put in a specific latitude and longitude, and choose a time subset. Pick a particular level. In this case, I guess we're just picking. Oh yeah, we're picking wave heights in this case. So we're going to go back to that same case we were just looking at in nCWMS and pull some data for this storm coming up the coast. We don't pick a vertical level because there is none. But if there were, you could select the vertical level. We pick a CSV output format, and boom, you've got the CSV time, lat, lon, and the wave heights here. And the cool thing about this is not only is it obviously simple to use CSV file, but the request is actually, if you look at your URL, after you click that button, it's got all that information right here in the URL. Time start, time end, and latitude and longitude. So you could just put this into any Excel. You can pop this URL into your Excel spreadsheet, change the latitude and longitude, and you've got a brand new extraction of data at the time you cared about, change the time extent, and you're looking at a new storm. That's pretty cool. And here it is in Excel. Actually, just you can go File, Open here, and drop that URL, and it'll open right up. Actually, it'll open right up after you change the default separator from tab to comma. I don't know why that is. Why didn't it figure that out? This is just showing that you can access it in any other tool. Here we've generated that same thing in a Python script inside a notebook, and there's the URL, and you can read it as a one-liner, right, and then plot it up. And in fact, we've done this for we're plotting up the observed wave heights in that green line versus the model prediction in blue. So we're doing a comparison of the model and the data at the location of this gauge. So we actually read the latitude and longitude from this gauge and pump it into this expression, pull the data from the model, and plot it. Dead simple. And actually this is sort of introducing also that you do something like this in the notebook, which provides the code, the Python code, and the output together. This is actually being done in Wakari, which is being done on the cloud. So you just log into Wakari, and it's got a full scientific Python distribution there for you to use. And so you can just go ahead and copy this notebook. Somebody who clicks this green, I shared this notebook by clicking the share button, and now somebody can just run and edit this notebook by clicking the green button. They click the green button if they've got a Wakari account. They just get logged in and they're running the notebook. If they don't have a Wakari account, they can sign up for free, and then they're running the notebook by just providing your username and a password. No credit card. For now, anyway, it's free. And if you want more memory, you can pay a little bit more. So while we're on the notebook in Python, so we've shifted now. We have a huge Matlab community in oceanography, and that's probably not going to change as soon as we'd like it to. But we do have more people using Python, and everybody, I think, last time actually I asked how many people were using Python, and just a few people raised their hands. And I asked them, well, how many people would be using Python if you didn't already have all those years invested in Matlab? And like everybody. Everybody raised their hand because you know that as a scientist you want to be sharing your results with everyone, right? Not just the people who happen to have MATLAB licenses. So this is actually introducing a CF library for meteorology and climatology. So for Python. So we have a great. It's nice that in MATLAB we can use NetCDF Java because MATLAB can import Java. So we just layer right on top and we use all the great CDM stuff that's in Java inside MATLAB. Move to Python, not so. We would like to use libcf. libcf appears to be somewhat dormant. So instead we are using a Python-based solution which is being provided by the IRIS folks who are actually the British Met service. So they've got a team of I think it's 7 or 8 developers who are just going to be working on this for as long as it's not like it's ending next year or the year after that. They're just going to keep on working on this. If they're working on this for their own community of users within the British Met Office, but you can go get this on GitHub and start using it right tomorrow. And if you're working in Anaconda, which is a Python distribution, free Python distribution, which includes all these different packages, you can just say conda install iris, and you're up and running. So this is actually just showing going after some WaveWatch data, and you give it a URL, you say iris load, you get back these so-called cubes, but don't let that scare you. It's just a way that they call a variable with some metadata and the ability to retrieve its coordinates a cube. It's a little goofy, actually. I wish they wouldn't have done that because it sounds weird. But you can. But here are the different cubes it found, the different variables, and then you can just say, well, give me all the variables at this time and within this latitude and longitude range. Actually, give me a slice from that cube and plot it. And here we are plotting the wave height for this particular time and in this particular range. So it gives you all that same ability to do subsetting on space and time using the CF conventions. And so here's just proving that it works with all the stuff that we were just using NCTOOLBOX on. Here are all these different models that are running in IOOS, and all we're doing is we're providing a URL and the standard name, and then we can just use this same routine. It's just proving that no matter what the people name the variables, no matter what the vertical coordinate system, we can just use these things to retrieve. So actually, that was global HICOM. So this is a regional model, ROMS model. This is global HICOM. And this is some more models, and this is just, and if you can go edit this notebook too, and just verify for yourself, or if you're interested in what the sea surface temperature happens to be, you can just go run this yourself. So, I think the other big thing that's been made Unidata software so successful is it's so darn easy to install this stuff. 60 minutes. That's what we ended up basically, people usually have Java around. If you don't, I don't know if it takes 10 minutes. Probably about 10 minutes. Install Tomcat, 15 minutes. Well, that's if you don't, go through all the security stuff necessarily. But then dump your files in a directory. Take a look. Maybe add a little NcML if you're working with somebody who knows what they're doing. 15 minutes, and suddenly, it's like for people who have never seen this stuff before, it's like, oh my God, Suddenly, and 1 hour after, all they had was a collection of weird NetCDF files that they were using God knows how with their own funky software. And 1 hour later, they're looking at an animation in Google Earth that they created with nCWM. And it blows their mind. And so this was super easy sell. In fact, I think I might have mentioned the story before, but in one region, I was talking to the guy about how we wanted to install the THREDDS server. And after about half an hour, he still wasn't convinced. He said his sysadmin really didn't have enough time, to do this kind of thing. And then the sysadmin came back and said, "Well, I actually already did it." It's like, well, okay. So you take a collection of weird files and just with something as simple as this, aggregating along, the ocean time dimension, and give it a weird, a very special. Give me all the files that have wide and 4 characters between 0 and 9 and end with NC. Boom, you've got a data set that is an aggregated data set that you're serving here, and you're looking at the the data with nCWM. So moving on to the searching for data, I think this is one of the cool things that's happening now. It's given me like a reason to like actually care about metadata. Because these catalog services, this is GICAT, but this is the same picture as before, but flipped around in a sense that here's the common data model for metadata. Now it's an ISO metadata, and it harvests from all these different services. One of them is THREDDS. Harvests into this database, and then you can query this database with an OGC standard service such as CSW, ISO, or you can use something sort of community-based like that's not ISO based, or I mean it's not OGC like OpenSearch, although I think maybe OpenSearch is OGC now. Anyway, so what this allows you to do is to basically harvest your metadata from all these different THREDDS servers, and then you can use this is actually GeoPortal that we're using in IOOS right now. It's harvested all the metadata from all these different THREDDS catalogs all over the place, and then you can say things like you can search on like WRF or ROMS or COAST, which is our funny USGS model, not NGDC, and get back a bunch of results. And we've searched in a particular lat-long bounding box, and we get back a list of data sets. And we click on the data set, and we get a little abstract of what that's about, and we have the OpenDAP link and the WMS link. So, okay, well, you can find this as a human, dinking around in here, clicking around. But more importantly, you can go and use this through a programmatic interface in Python, say, to query for all those data sets that you want to find. So in this IOOS system test that we're doing right now, basically the idea is, okay, we've created all these services and we have these tools. Let's put them into play to do these end-to-end workflows that show finding data, accessing data, using data, analyzing data, visualizing data, all in a single notebook that we can then hand off to somebody, and they can take it and run with it and do science with it. So in this case, this is the very first one we did. It was looking at inundation, so water levels along, wherever you want to look. And so basically, you start off, you query the CSW service to find the data sets that match your criteria. You extract the OpenDAP data points from these model output, and you pull the data. It's just basically what I just said. And this is working with we've got a whole bunch of these. If you're interested in this, go visit this URL, github.com IOOS system test. We've got all these different environmental themes that we're fleshing out with these notebooks. And so this one, the user specifies a certain time, start time, stop time, and then it finds all the observational data that have water levels. In this case, it found all these stations in this region, so the user specified this region. And then it goes and gets the data from those services, and then it finds all the models that are in that region, goes to the models and extracts time series from all those models. And so at each observational location now, we're looking at water levels from observed data in the dark gray, and then all these colored lines are different models. And this had never been done before, because it's just too much work unless you have tools like this. So, and as soon as we did it, we realized, oh, actually, there's like common offsets here in these models. These models, some of these models have not paid attention to vertical datums too much. And so Felipe, actually, do I have him? I think I lost Felipe. Oh, anyway, Felipe Fernandez is working on these notebooks in Brazil under IOOS funding. He's an awesome Python dude, and he's sort of taking this to the next level where instead of just creating a static map like I showed on the previous slide, he's actually using Python to generate these interactive maps in Folium, using Folium, I think, where if you have this live, you can zoom in until you see the dock on which this station, this tide gauge is. And when you click that dot and click that tide gauge, you get these plots comparing model and data. And these are live too. And then in the same notebook, he's producing these nice-looking tables that show us these biases that the models have at different locations. And based on this, we can go to this modeling team and say, you've got a problem. You're positive by at least 20 centimeters, or around 20 to 30, 40 centimeters at all the gauge locations. And a lot of times it's because the way they're assimilating altimeter data or using their open boundary conditions. So by using this tool, we're going to get better models. And he also actually, and this is kind of cool, so inside the notebook, it's not just limited to Python. You can actually use a Matlab magic if you want and do Matlab inside one of these cells. Or you can do R, or you can do any of a list of about 30, use about 30 different languages or tools inside the notebook and mix it with Python. So in this case, Felipe, he said, well, I know the NetCDF Java library is doing the right thing for these vertical coordinates. So John's wondering if it is. So he wanted to code these vertical coordinates into the IRIS package. And so here he's just calling MATLAB and passing in the URL using our NcTOOLBOX here to return the vertical coordinates for salinity at a particular grid cell. And then here he's just plotting this up on the Python stuff that he did using IRIS just to confirm that these two lines are falling on top of each other. That's pretty cool because you're using NetCDF Java behind the scenes here to do this MATLAB stuff inside the IPython notebook, and then you're doing Python, which is using the same CF compliant data set but through NetCDF for Python. Anyway, I think that's cool, but I'm kind of a nerd. All right, so in terms of Unidata challenges, I think the stuff is fantastic. We've actually, some of these have been mentioned in our user committee meetings, but the robustness of the THREDDS data servers, now that people are using them operationally, we care when they go down. So we need to find ways to make those more bulletproof throughout our community. I'm worried about support as the popularity increases of these things. If THREDDS servers take over the world, how do you handle support for that? Maybe it's through letting the community support itself. Like that's the way most of these things go. UGRID, I want to see that unstructured grid stuff incorporated into NetCDF Java. We actually have a proposal going in that maybe would address that. Aggregation of large collections of NetCDF files, I know that's on the list. These MetOcean tools developed for Python. How do we get there? Do we use IRIS? Do we come back with libc library that then could not only be used in tools like Python, but could also be used by R users? That would be nice. I think it would be cool to have an IDV-like client built on top of Python tools so that you have the functionality of IDV, but underlying that would be functions that anyone could call to do cool stuff, maybe develop their own GUI or just to do analysis using all that kind of same, powerful analysis components that IDV has. And, participation in standards, I know you do this already. Just want to make sure that you guys keep it up because you have a really important role there to play because you are building software that actually uses the standards as opposed to just sort of sitting around a bunch of standards people deciding what might be good. Developing the standards alongside of the tools that actually work, I think, is a really key part of getting useful standards. Okay, so, actually, this is a, I know you're moving more toward the community development, and this is a cool thing where it turned out that the places like data.gov, if you did a query there, you would get back OpenDAP links and WCS links, but it said scheme equals none, which meant that you couldn't figure out what those links were unambiguously. Well, one of the guys in IOOS figured out that was due to something in NC-ISO that Unidata has taken underneath the THREDDS umbrella in GitHub. And after I complained about it, the developer for the PyCSW, which sits behind data.gov, he gave a thumbs up saying, yeah, that would be a good thing to fix. And then this guy, Pac IOOS, fixed the problem, and he submitted a pull request. And then, so he submitted this pull request to fix the problem on GitHub. Tom writes back, huge, another thumbs up. And then another user, Dave Neufeld from NGDC, actually closed the pull request. So he merged so here you have data sitting on Unidata's website in their GitHub repository that was totally, Unidata was watching, but the issue was raised, the problem was fixed, and merged by all non-Unidata people. And I think that's pretty cool. Maybe you guys think it's scary.
We think it's really cool.
Yeah. So I think it's very cool. So, why do I promote Unidata technologies in general? I think they're powerful, they're flexible, they're easy to install, they're free, and they're supported. Free and supported. That's a powerful combination. A lot of times you have free, very rarely do you have supported. And I think it's driven by a community of users, which I think is really important too. And now some of you, these next few slides, some of the staff might have seen before, but I like them so much that I'm going to show them again to illustrate the kind of community that Unidata has. Because sometimes you don't realize how the people are, the community are so vociferously advocating for these standards. And, and you can go, actually, oops, no. And so, I don't know if you can see that, but you find the support for the community in very, sophisticated environments. And it's also made its way down. It's in very high-tech environments, and and down to the man on the street. It's got wide-ranging support, and even unexpected appreciation in places you wouldn't expect. So
is that GI cat?
Right. So in summary, I think this is I am still very excited about all this stuff. And so not only have we got common data models now for structured and unstructured model grids, we've got them for time series, profile, swath. We've got like 80%, of the stuff that we do described in a common way. And we're building these standard web services for working with this stuff and the metadata that allows us to do these kind of catalog searches. We got the whole thing. So what we need to do is build tools that work with these services and deploy them to users in R, MATLAB, Python, ArcGIS, JavaScript communities. And this is the thing that actually we're a little bit weak on. We got all the standards and the services. We need to deploy them more, and then we need to work on these tools. It's great that we've got this little NCTOOLBOX, but it's sitting there now unfunded. It's great that the Iris guys are working on it on the Python part, and who's helping the R people? So, my last slide here, it's easy to, deploy this stuff. It's awesome. If you haven't done it, do it. And what you get is you get all these different choices for data access, from everything from IDV, 3D visualization IDV, right down to Excel. You get more people looking at your stuff. You get more feedback. You increase your code, your shared community, sharing the workload with the community. Hopefully, we get more support for the standards-based approach. Less time dinking around with data, and so. Basically, if you see somebody writing software that's not using this approach that should, please let them know and support the development of tools that use this standardized access, and we'll get better models, and we'll get better use of observational and modeling output, and we'll make a better world. That's it. If you want more info, github.com. Thanks. Thank you.
Black hat.
Nice.
So thanks very much, Rich. And we'll open the floor to questions. And just raise your hand, and I can pass the mic around.
That's fine. I can just talk.
No, you're being recorded.
Okay, quick question. Just like the first slide, the title page you show, which is 3 different data sets, but still based on MATLAB.
Yeah.
So I was just wondering, is there any other way, like Python, that can eventually replace that kind of plot, so I don't need to buy MATLAB?
Oh yeah. So that was showing MATLAB because that's where we started because of NetCDF Java, and it already provided all that functionality. But now you can do the same thing in Python with Iris for free. Tomorrow, you can just go and install the Anaconda Python distribution, which makes it easy. It's free, and it has 200 packages already included, and you can install Iris from the bin star, from a channel. So the cool thing about Anaconda is that people can upload packages that are kind of strange packages, Python packages. You might view the Iris package as a bit strange. It's hard to compile if you just get the code, but you can basically build the package and then upload it for everyone to use. And so you can just install it from the BinStar, using this BinStar site that has all these packages, you can just install it from that package. And whether you're using Linux, 64-bit or Mac or Windows, it just is a conda install, and you're able to run that very same demonstration that was shown in Matlab on the first slide. Because really, what's key there is that those providers have provided their data in CF compliant format through OpenDAP.
Having seen the NetCDF Java that you then use NCTOOLBOX for in MATLAB, when I think of NetCDF Java, I think of translating from other files. So could I take, say, a Genpack file, pop it into a Python script, and use Iris and, save the world?
A Genpack file?
Yeah, and use NetCDF Java that would convert it into NetCDF.
Yeah. So if you had you could certainly read it with NCTOOLBOX. I don't know if you could read it with Python yet directly, but you could read it into a notebook using the same approach that I did with the MATLAB magic cell and NCTOOLBOX working behind the scenes to read that, because then it would be using NetCDF Java, and then it would be reading the Genpack. I think it would be cool to have a Genpack magic, so you could start using Python, but you could still be using your Genpack stuff and integrate that sort of together. No? No? Well, maybe not. I don't use Genpack, so I don't know.
I think it would be cool.
Yeah.
For reading Genpack files, you could also use the OpenDAP from a THREDDS server. So get Genpack file posted on a THREDDS server somewhere. You can use Python, NcDF or Python to access it over OpenDAP or something.
Yeah, actually, we use that a lot, just to even for local consumption. Like if we get a bunch of GRIB files in, we'll just toss them on the THREDDS server and access the OpenDAP aggregation instead.
More questions? Okay, we've got 60 minutes, so let's install. Let's do it.
Okay, yeah. So actually, if any of you want to install THREDDS server, I did this for the IOOS people. If you want to call me up, and I'll just sit there and we'll just do it. Open up a WebEx and just do it. Feel free. I mean, it's not that much of my time, and it's really it's easy, and it may not, except the security issues might not, and then you can go back and ask Unidata how to make it really secure.
Don't put it on the internet. Just let it be a private server on your own local network, and you'll be fine. If you're going to open up to the internet, then you have to go to the security hardening. And that's more or less, that's a lot of what we teach at the workshop, THREDDS workshop. So if you do need to do that, you really don't want to do it without, and not secure it.
So maybe the approach would be, do it locally first, convince yourself that it's cool, and then spend the hour to do all that, and then if you think it is cool, if you don't think it's cool, then you're done. And if you do think it's cool, then you spend the extra hour to go through all the security junk. Because that's probably about how much it would take, right? Another hour?
Yeah, it depends how experienced you are, and it's also, you're going to have to get your own system admin / security people involved, but assuming that they're willing to do that, or you have that skill, it's about an hour's worth of hardening Tomcat. Some institutions are already running Tomcat servers, so you've already done it. You can run THREDDS, you just drop the WAR file into your existing Tomcat server if you have permission from your admin people. But government's pretty tight, and EDUs are less so, but still it's a good thing to keep it private at first.
Any last comments? All right, thanks again, Rich. Let's have another hand.
All right. Thank you.